Our last integration technique is called partial fractions. And this is for integrals of functions of the form f of x over x minus a times x minus b. And really, this isn't an integration technique at all. It's more of an algebra technique. The idea here is to see if we can rewrite the integrand as some quantity a over x minus a plus another quantity b over x minus b. And the idea here is that if we were to add the two fractions, a over x minus a plus b over x minus b, then we would have to find a common denominator. And that common denominator would be x minus a times x minus b. And so we can think about the integral that we want to compute as coming from these two separate fractions. Now, this technique is best illustrated by doing examples. So we'll look at an example. In this first example, we want to do the integral of 1 over x minus 1 times x plus 1. So we're going to factor the bottom to get it in that form. And then our goal is to rewrite that as a over x minus 1 plus b over x plus 1. Okay, so I need to look at a over x minus 1 plus b over x plus 1. And I need to think about how would I combine those two fractions to, and the way to do that is to find a common denominator. I would have to multiply the top and the bottom by x minus 1 for that second fraction, and then I'd have to multiply the top and the bottom for the first fraction by x plus 1. And so what would happen here is I would get that a times x plus 1 plus b times x minus 1 would be the numerator of my combined fraction, which has x minus 1 over x plus 1 in the denominator. But I know that that's supposed to equal 1 over x minus 1 times x plus 1. So the two numerators must be equal. So it must be that ax plus a plus bx minus b equals 1. But I'm not going to think about it just as 1. I'm going to think about it as 1 plus 0x. In this case, then all the x's need to match. So ax plus bx would need to equal 0x because the x's, the coefficients of the x's would have to match. And then the constants would have to match. And this would tell me that a minus b would have to equal 1. At this point, we have two equations and two unknowns, and so we can solve for a and b. It looks like it'll be easiest if I just think about b as being minus a, and then I substitute that back into the second equation, which tells me that a minus a is equal to 1, which tells me that 2a is equal to 1, which tells me that a is equal to a half. Well, if a is equal to a half, then that tells me that b, which is minus a, must be minus a half. And so now I have that my integral of 1 over x squared minus 1 dx must equal the integral of 1/2 times 1 over x minus 1 minus 1/2 times 1 over x plus 1 dx. Okay, so we're going to integrate those. So I'm going to get 1/2. And then the antiderivative of 1 over x minus 1 is just natural log of x minus 1. Make sure you include absolute values because you should remember that the antiderivative of 1 over x is the natural log of absolute value of x. And this is going to be minus 1/2 times the natural log of x plus 1 and plus c. So that is the antiderivative. Sometimes you will see some people decide to combine these using log rules, 1/2 natural log of x minus 1 over x plus 1 plus c. But that's not necessary. It's just a manipulation that you might see. You might even see some people take the 1/2 power or the 1/2 out front of the natural log and move it to be a power there, but that might be a little bit excessive. So we'll go ahead and leave it the way it was before. Okay, let's do another example. Okay, so in this case, we want to integrate x plus 2 over x squared plus x. So I'm going to rewrite this as x plus 2 over x times x plus 1 by factoring the bottom. And I want to rewrite this as a over x plus b over x plus 1 dx. Okay, so what I want to say here is that a over x plus b over x plus 1 can be combined using partial fractions. I'll multiply the second one by x over x, and the first fraction by x plus 1 over x plus 1. Then I will find the common denominator there, so that I get a times x plus 1 plus b times x all gets divided by x times x plus 1. And I know that that's supposed to equal x plus 2 over x times x plus 1. Okay, so looking at just the x's, that tells me that a plus b is supposed to equal 1. And then looking at the constants, that tells me that a is equal to 2. Okay, well, if a is equal to 2, then b must be minus 1. So that one was rather simple. So we're going to do the integral then of x plus 2 over x squared plus x dx. And when we do this integral, we're going to rewrite this as 2 over x minus 1 over x plus 1, substituting in a and b dx. So the antiderivative of 2 over x is 2 natural log absolute value of x, and the antiderivative of 1 over x plus 1 is natural log of absolute value of x plus 1, and then we're going to add a c. I'm not going to combine those because those don't have the same coefficient out front. Okay, let's move on to our final example. That is the integral of x over x squared minus 1. And you might follow blindly. You might start to say, okay, I'm going to do the antiderivative of a over x minus 1 plus b over x plus 1. But I encourage you instead to look at that integral and ask yourself before starting, could I do that in a simpler way? And I believe the answer there is yes. I think if I let u be the bottom, x squared minus 1, and du equal 2x dx, then in fact, x dx is going to be 1/2 du. So I can use the u substitution method. Okay, so this becomes the, let's see, the antiderivative of 1 over u, and then the x dx becomes 1/2 du. Oh, this is much simpler because then this is going to become 1/2 natural log of the absolute value of u plus c. And then if I substitute in for u, it's going to be 1/2 natural log of x squared minus 1 plus c. Now, I believe you could have done partial fractions, and you actually could have gotten the same answer, but it would have taken a lot longer. So don't just assume, because you see something that's a fraction like that, that it has to be done using partial fractions. Make sure that you look for alternatives, like use substitution, or other alternatives that might pop up before moving to partial fractions.